All right, good morning, everyone. Let's get our screen set up. Okay. There we go. Okay. So we are getting close to our second test already. We've got two more sections, one today, 12.3, which will be second derivatives. And then this is Thursday. Then on Tuesday, we'll take a look at related rates, which is 12.5. Remember 12.5, the related rates takes us back to 11.6, which is implicit differentiation. That's basically, we'll use that implicit differentiation to solve related rate problems. And what a related rate is just like a circle. We know how the radius is growing on a circle. The related rate is that affects the growth of the area. Not linearly. We'll see it's according to the formulas and stuff. But as we know, as we can measure how one thing is changing, it tells us how something else. So like, on oil spills, that's how they do it. They get the rate that the oil is coming out, and that tells them in a couple hours, that's how big the oil spill is going to be using related rates. Can use it for other things too. How many people are, going into a soccer stadium. So we got the rate of people coming in, then we can also tell what the rate of the fill up is, all that kind of stuff. What I talked to my other class about yesterday was I'm going to do something a little different for the test preparation this time. We do still have our review, which is provided by the course coordinators. So that's kind of down here. I do have we used to have a review in WebAssign. They seem to have taken that out. But what I did is I solved all 40 problems. So those are there. So you'll see me solving. So you can look through those. I think it could help with some of the homework problems because that made them sort of like that. The tests are not in WebAssign, so they're kind of different. So I guess they decided to just not put the WebAssign review up there anymore. But since I still have the videos, those are there to help you. And I did them, I think, in blocks of about 10 questions. So you'll just have to kind of go through till you see something that might be helpful for you. What I will do, though, is I will work on doing videos for the actual study guide, which is up there. It does have an answer key, but I'll work on that. The other thing I'm going to work on is doing a online quiz, which you can take repeatedly until you get it all right. I'm going to take questions from a previous exam, change them a little bit, but I will focus on the open answer, the essay type questions. However, I will provide some multiple choice for them, so there'll be like 4 or 5 questions. You'll get some practice with multiple choice. You'll get some practice with writing the open answer, and the way I'll deal with it is once you've submitted your answer, I will show you how I worked with it. So what does work for this type of thing look like? So then you can kind of see, you can learn from doing it that way. Okay, and again, you can take it multiple times, but the goal is if you take it as if it was a test question, get it right or wrong, whichever way you go. If you get it wrong, work it again until you get it right. And you'll still be able to get all the points for the quiz, the 50 points for sort of prepping. Still want you to go through that review. I might even take some of those review questions, put them in there, but also give you that option to kind of take a mini test to see what it's like, okay? And work on developing those skills of when we say show your work, what are we talking about? And so I'll try to maybe even give a couple options, but we'll try to do that because I'd like to see as many scores in the 90s as possible, right? So because we can do real strongly this time, then we just keep on going till the end. After we finish this, we are done with sort of the forward part of the course. We're done with derivatives, rates of change. We're going back the other way. We will start with rates of change and get back to the function they came from. So we're going to basically start with derivatives, take the antiderivative to get back to where we started. So if you've, whatever you've picked up from this part of the course, we'll just start doing most of it backwards, which again will actually help build understanding as we go through that. Any questions or concerns as we move forward? All right, good to see you all here. Again, we do, I've got this recorded, so we do record that, but I also want to let you know I appreciate each of you for being here. It helps me. Hopefully it helps you as well to be in person. But when you're not able to, we'll have the recorded sessions, and you have both Tuesdays and Monday, Wednesday lectures. You see which one I do better, because this is the second time through, so sometimes I might do yours a little bit better because I did theirs first and thought of some things, and sometimes I'll even add some things, but oops, let's back up. The thing is today, the lesson, there is no new skill. We are not learning any new skills. We are at the very most, all we're doing is we've got a function, we take its derivative, and then we take that derivative and take the derivative of it. So we have a rate of a rate. So what does that mean? Most of what we're going to do is to try to make sense of what we're getting. So the one we'll start off with is we'll have a function that gives us our position. And what that means is if the function tells us after you've been driving your car for 2 hours, you know how much distance you've gone. That's a position function. If you take that derivative, what do we get? So the first derivative gives you how many miles you traveled. The derivative gives you the rate, so it's going to give you miles per hour, right? So you could figure out that. So what would the derivative of the derivative give you? So what's the rate of the rate? So you know your speed, your velocity actually is just directed speed. That second derivative is acceleration. So, if you've got that sports car, you step on it, you go back like that's acceleration, right? That's the second derivative. First derivative is just speed itself, which could be constant, but second derivative is that feeling of either back, or it also could be negative, right? Negative acceleration, you start braking, you go the other way. That's acceleration. That's the feeling of acceleration. So I think I mentioned this earlier. One of the best ways to really understand all these concepts in calculus is to take a ride on a roller coaster. Because you get first derivatives, your speed, you get your second derivative, which is acceleration, either up or down. You get it all. Okay. And we're also going to see that we can use that second derivative, how the rate is changing, to as another tool to figure out when we get a minimum or a maximum. We get an extrema, right? We take its derivative and set it equal to 0. We know it's either a minimum or a maximum, but from that alone, from that one test, taking its derivative equal to 0, we don't know whether it's a minimum or a maximum unless we look at the graph. This will give us another tool that we can do. We can take the second derivative and see what sign it is, and that will tell us whether it's a minimum or maximum. So that's all we're going to use it for. Again, no real new calculus skills, just the ability to take the derivative of the derivative. Okay, so this kind of gets into what I was just talking about, is that we start off with a position function, right? Some function s of t, and I'm not sure why they use s of t, maybe in German or something. Sometimes that's what it is these engineering were done in some other language, and s, I don't know if s in German distance starts with an s, but I would use d, but anyway, they use s all the time. That's our position function. When we take the position function's derivative, we get the velocity, which we think of as directed speed. So it could be positive or negative, depending upon which direction we're going. That's what velocity is. Velocity is speed with direction. Okay. So, and that's the thing is we think of in algebra, we usually would have problems where the speed, the velocity was constant, because that's really all you can do with algebra. But with calculus, we've got rates, so we can talk about what it means for the rate of change to change. We can talk about what if you've got something that's changing, and that gets into acceleration. So that's when our speed is not constant, and that's a reality, right? We're on the freeway, we might be trying to hold a constant, but rarely do we do it even with cruise control turned on. If we hit a hill, we'll probably have to speed up a little bit to keep up on that speed and down. So actually things change even with that. But if we then take the derivative of velocity, what we end up with is that acceleration, which is whether we're speeding up or slowing down. Okay, so and it's got weird units that are, I don't really understand, but you'll see that what's the units on velocity? If we're talking a car, it's miles per hour. And then what is it going to be? So this is velocity. Acceleration, is going to have units of miles per hour squared, because it's, and again, don't ask me to explain it, I don't really understand it, but it's just that it's not speed itself, but it's how the speed is changing. So you get this extra unit in it. You can kind of understand it where it comes from the math, but physically, I mean, again, we understand what it is. It's that, if you step on it, then, your head goes backwards and hits the window behind you. If you step on the brakes, you fly forward. That's the feeling of acceleration. Okay, so what we see is if we're starting with the position function, that to get to the acceleration, we have to take two derivatives. And that's one way of mentioning it or indicating it is putting two primes. So it just means take the derivative of the derivative. Okay, so you're going to have some, and we'll do a few example homework questions. And the homework question will just say, here's your position function. What's the acceleration? And you just have to know there's that in between. You have to take two derivatives to get there. You can't just jump to it. Although sometimes they seem to, that's what they're doing. Okay, so we'll just take the second derivative and hope, and again, it makes some comments that there's some functions that I guess you can always keep taking its derivative. Remember, those sum functions, if we get to a constant, you take the derivative of a constant, you get 0, right? So if you had if your speed was constant, you take that derivative, your acceleration is 0. You're not getting faster or slower, you're staying constant. So that's a possibility that the second derivative is 0. But if you've got a function where velocity is actually changing, you'll get something different. Okay, so here's a quick example. They give us a function, and we'll just talk through this, x to the third minus 1. To take its first derivative, we see x to the third becomes, the 3 comes down, subtract 1 from the exponent, you get 3x squared. The derivative of negative x is just negative 1. So now we say, okay, I've got that first derivative, how do I take the second derivative? Well, I just look at it as a new function. What's the derivative of 3x squared? Well, the 2 comes down. 2 times 3 is 6. Subtract 1 from the exponent, we just get 6x. Derivative of negative 1 is 0. So our second derivative is simply 6x. Okay, and if we wanted to find what the acceleration, so that would work if the first derivative was a position function. The second one is a velocity function, which would give us our speed. The third function, the second derivative, is the acceleration. So you can plug in a value and you get your, so I guess at negative 2 seconds our acceleration was going down by 12 So we were putting on the brakes, we're slowing down, something like that. But that's all we're going to do is we're given a function, we take its derivative twice, and then that's how we're going to get acceleration. Okay, and again, a quick example down here, we'll actually go through a homework problem, but you start off with a position function, you take its first derivative, that gives us velocity, take that derivative, that's your acceleration, that's what we're going to be using in here, and if they give you a value, you plug it in. If not, it's a function. Okay. So here's one from the homework, and I think there's maybe at least 2, 3, maybe 4 more of these type questions. They just give you different functions. You'll see that this one will just have different values wherever the red numbers are. So all it says is find the point's acceleration as a function of t. This is a place, there was one like this on the last test. Some of you were trying to figure out what the number was, but what they want is they want the function, and it could contain a t. It could contain the variable. It's not at a specific point. The second question wants you to find that derivative at a specific point. Okay, so again, it doesn't say find the second derivative, but since we were given the position function and we want the acceleration function, we have to take 2 derivatives. So we go ahead and take the first one. Derivative of -12 is 0. Derivative, I guess I could put that here. Derivative of t plus t is going to be just 1, right? 1 t to the 0 if you wanted, so that's just 1. So I took that derivative. And then the derivative of -18t squared, the 2 comes down, so we're going to get -36 t to the first power, 2 minus 1. Okay, so we took the first derivative. But we don't even use that, right, because we want the acceleration. So now we're set, but we had to get there to get the second derivative. Now we're going to take the derivative of the derivative. Well, 0, that's gone. Derivative of 1 is 0, so notice that disappears. Derivative of -36t is just going to be -36 t to the 0, which is 1, right? So the acceleration itself is a constant. So, and it's negative, so I guess we're putting on the brakes. That's all we can say. And so, again, it's weird they want it in terms of t, but in this case, the function is a constant, so s of t is equal to -36. So we put that in. Find the point's acceleration at the specified time. Well, at 4 seconds, since acceleration is a constant, it's still -36. So again, where do we plug in the t? Again, you could think of it, and you could probably put the answer here. This could be t to the 0. You plug in 4 to the 0 is 1, times -36 is still going to be -36. Okay. You'll see on some of these, they'll give you a function that starts with maybe like t to the 3rd power. So they might give you s of t equals 4t to the 3rd. And then when you take its derivative, right, 3 times 4 is 12t squared. And then the second derivative is not going to be a constant. It would be 24t. So it's possible for there to be a t. It's possible for it to be a constant. It's even possible if the position function is a linear function, by the time you take that second derivative, it's 0. So you really have no acceleration. So those are all possibilities depending upon which function you start with. Does that all seem to make sense? It just follow along, take the derivative of the derivative. Sometimes you'll end up with 0, sometimes you'll end up with a constant, sometimes you'll end up with some t left over and you actually have a variable function. Okay, so a number of different ones to try just like this, and basically all they really do is change out the function. So that's one major application of the second derivative. Physical, it's the acceleration. So that's for all your physics folks. Business, I don't know that we use it all that much. Although some of you that are going into finance, with the stock market and stuff, they have things called derivatives now, which are not the investment themselves, but they're kind of getting into this. And you can even, they've got things where you can even bet against something. They call those. So there's a derivative. You can buy derivatives of a stock. You can buy shorts of a stock, so you're actually buying for the stock to go down. So they've got all these different things that kind of involve these rates, and it's a brave new world, I guess. So here's some notation. So, and again, you won't have to visit, you could shoot, when you have to write it out, you can do it either way. I tend to favor this second derivative, just put another prime mark. That's my favorite. This one you'll see in the homework, and just kind of don't worry too much about it, that this 2, where that 2 is at, because they'll put it up, but it just means take the second derivative. Okay, they give a little explanation down here. It's sort of, you're taking the derivative, so we usually use d of y, dy dx, right? Here's df dx, and when you take that derivative, you're getting, a d squared in the top and 2x's in the bottom. Again, it's just a way of writing it, so when you see it, know to take 2 derivatives, right? So what does that look like in the homework? They'll just tell you, take the second derivative. So if you're given a function, you've got to do it twice. Now, again, they just jump from the example to here, but again, for the calculation purposes, you've got to take the first derivative, which is the 3 comes down, x squared, and then you can take the second derivative, which is the 2 times 3 gives us 6, subtract 1, you get x to the 6th. Again, some of you if you could do it in your head and, sort of seem like you're skipping that first derivative. I mess up when I do that. And you see when I work with you, if I don't do each step, I'll be off by a negative. I'll leave something out. So I found it's always best just to go through all the steps, even though sometimes the book throws something like this at us. And so in the homework, again, there's several of this, and they just ask us to do this. You just have to look at that. Oh, they want the second derivative. So I got to take the first derivative to get there. That's not what they want, though. They want me to take the second derivative. So something like this, again, just do what we've been doing. Use algebra to rewrite this, minus 4x to the minus 2. So get that exponent, the negative exponent. We're going to leave it up there for a while. We take its first derivative, so this is something we've been doing. So negative 2 times negative 4 gives us a positive 8. We subtract 1 from the exponent, so that's going to give us a negative 3. So that's the first derivative. And then now we just do another step. We take the derivative of the derivative, and so negative 3 times 8, negative 24. Subtract 1 from 3, we get x to the minus 4. And that's a good answer. I think it'll accept it just fine. If you want to rewrite it, you could move the negative 4 back down. So negative 24 over x to the 4th. And I think that's some good practice. I've seen, again, some of you will take that negative 24 and move it down into the basement as well. But remember, the negative exponent only applies to the x, so that's the only thing that goes down. So, practice a little bit with these. So again, just the derivative of the derivative. Nothing new, it's just one more step. So far, so good? Okay. Acceleration due to gravity. Here's another place where we use this. Basically, gravity on Earth, at least, is pretty much the same wherever we go. Now, I guess if you go up to the top of a mountain, it might be a little bit different than at the bottom of Death Valley. If you're into physics, you might know that, but it's probably a minuscule difference. So wherever we're at, if you drop an object, it would fall at a rate of negative 16t squared. So this is a position function of, you drop it off a bridge, how fast it's, or where its position would be. If we take the first derivative of this, what we end up with is negative 16 times 2 is negative 32t. So that's going to be the speed of this little object. And again, it's doing it in a vacuum, so that means that air resistance doesn't matter, or at least there is no air resistance. If you've ever watched those guys who jump out of planes, what do they call those? Parachuters or skydivers, right? They go like this, and that'll slow them down because that's air resistance. This doesn't take into, this is just gravity. Or they go into a ball if they want to go fall a little bit faster. That's as fast as you can fall. So this is taking away air resistance. And so what this is telling us is that as this object falls, its speed changes. The longer it's going, the faster it's going to be going down, right? And then when you take its second derivative, which is on the next page, but I'll go ahead and do it here. The second derivative, which is going to be acceleration, you get that acceleration is a constant. So you are accelerating, and again, that's negative because its direction is downward, but you get to something called, and actually I think skydivers get to a place after you've fallen so long, you get to what they call terminal velocity. You only fall so fast, and then yeah, you're going fast, but you don't go any faster. But that's partly because of air resistance. But this just tells us that acceleration due to gravity on Earth, at least, is negative 32 feet per second per second. And again, that's where it kind of feels weird. What is that second squared, right? Here it is. So the units are kind of different, but it does let us know it's not speed alone. Speed is just feet per second. That's speed. Feet per second is acceleration. Okay, so acceleration doesn't change. It's a constant. And it's got a downward velocity. So that's another application. Again, if you took the derivative of acceleration, what would you get? I have no idea. So we don't do it. So it would be zero, whatever it is. But I don't know what we would call that physical property anyway. I think that's pretty much it. Oops. Yeah. So acceleration due to gravity. Good. We're good shot. So here's the other application of a second derivative. Remember, it's the rate of change of the rate of change. It's how the rate of change is changing. So if we look at these two functions, f and g, which one of those is increasing? Is it f or is it g? F is increasing. Anyone think g is increasing? Hopefully you do, because it was a trick question. They're both increasing, aren't they? Yes. So they are both increasing, but one is not only increasing, it's getting faster, right? If we think of this as speed. F of x is the one that its rate of change is also increasing. It's accelerating, right? It's getting faster as how it's increasing. G of x is something that's still increasing, but it's slowing down. Its rate of change is slowing down. So there's these two types of increase. They're both increasing, but the rate of the increase is changing on us. One is increasing faster and faster and faster. The other one's slower and slower and slower. And the way we can kind of think of this is, let me see if I can do this well. If we were to draw a tangent line, say down here, and then we compare it to a tangent line up here, right? The second tangent line is steeper than the first. It has a bigger, its slope would be bigger, right? So if you subtract them, the second rate of change from the first rate of change, you get a positive value, right? Because you get a bigger number minus a smaller number. And so what that means is what we did is sort of an average rate of change. The rate of change is that the second derivative of this function is going to end up giving us a positive value. The rate of change of the rate of change is positive. Does that make sense? Because as your tangent line, slope of the tangent line gets bigger, a bigger number minus a smaller number will always be positive. Over here for g of x, the opposite is happening. We could draw a tangent line. Let's see if I can do this down here. It's about like that steep, but by the time I get up here, it's less steep, right? Those tangent lines, so it would be a smaller value. The slope would be, it's still positive, but it's smaller. So you take a smaller number minus a bigger number, you're always going to get something negative. And again, we're not so concerned about the value itself, just that the values, as we move along here, the second derivative here is always going to be negative. Because, as we go from one to the next, slopes are decreasing, slopes of the tangent line are decreasing, so that's going to make the second derivative negative. And so what this allows us to do is to do something called a second derivative test. Remember, we do the first derivative. If we find where the first derivative equals 0 for either one of these, we will find a critical point, or critical x value, right? And what we know that's happening at that critical point is we have either a maximum or a minimum. But when we were doing this, we didn't know whether it would be a maximum or a minimum unless we looked at the graph or plugged it in and compared it to other stuff. We don't know just from the first derivative is equal to 0. But now what we can do is we can take the second derivative and figure out whether that second derivative is either positive or negative. If the second derivative is positive, means the graph will look something like this, a parabola, an upward parabola. And the way I remember it is it looks like a smile, and you smile when positive things happen to you, right? So the positive, and hopefully I don't mess it up too much, but positive means we've got this smile. What are we going to get? Are we going to get a minimum or a maximum? Well, our point's down here, it's got to be a minimum, right? So if the second derivative is positive, it means we have a minimum. So now we have a tool where we can find out whether it's minimum or maximum without having to go to the graph. Again, for us, we got graphing calculators, so we could go ahead and graph it and take a peek. But again, when I was learning this in the 1980s, we didn't have graphing calculators. We had to use these tests. And I remember I always got them mixed up. Over here, what's happening when it's negative? Well, we get this thing called a frown, right? Negative things make you frown, or sad, or whatever. And so that is going to result in a maximum because of this kind of a function has a top. So if we've got a negative second derivative, that's going to tell us that extrema has to be a max. Okay. So again, just a second, it's a way to do it. We can also just graph it and see it. And I really strongly encourage you to do both. And whichever order you want to do it in. If you want to kind of peek first and look at the graph and say, oh yeah, that's a maximum. Oh, I'll take the second derivative. It's let's see, second derivative is negative. That's why. And you'll start to connect those two, hopefully. Okay, and this is just putting it in words. So the first one, the derivative starts small but increases, so the rate of change is increasing, and thus the second derivative must be positive, and positive things means it's going like this. This is the g of x, shows that the rate of change, the first derivative is actually decreasing, it's slowing down, and so that the second derivative must be negative because it's going like that, it's slowing down, and so we'd have when this happens, we get a maximum. When this happens up here, where it's positive, we get a minimum. Okay, and we put some more names with this. We call this concave up If concave up means it's like a wine glass ready to get some wine, right? It's up there. Concave down is when you're storing it, so you don't get any dust in it. So those are the two words we use for them, and it's because it's got this concavity. And sometimes they're not full U shapes, sometimes they're just like, that's concavity. So this is concave. Oops, I guess I should put that. This is concave down. This up here would be concave up. And then the other thing we're going to throw in here is that concavity can change. So whenever we change concavity, so maybe we start off concave up and then we go concave down, so we get this S-curve type thing, we get what's called a point of inflection, which is where it changes from concave up to concave down or the other way around. Okay, so let's think through here. This is concave up. So what's the sign of the second derivative? Is it positive or negative? Concave up, smile, positive things are happening. Up here, concave down, we're frowning, negative things are happening. How can you go from being positive to negative? Someone ruined your day, I don't know that. But how, mathematically, what happens when you go from a positive number to a negative? What do you have to pass through? Got to go through the border, right? What's the border of positive and negative? 0. Exactly. You have to pass through 0. And so what we're going to find is this point of inflection is the place where the second derivative equals 0. Or it could be. Sometimes that second derivative is not an inflection point, but usually it is, and the stuff we're going to be dealing with. You can also kind of see, because again it's a visual thing of concave up and concave down. It's kind of halfway between the minimum and the maximum, because right, if it's concave down we've got a minimum, if it's concave up we've got a minimum, concave down we've got a maximum. And when you see those, you see that happening, you kind of can see, okay, somewhere about halfway between there, that's where the inflection point is going to be. So in the homework, they will give you a few graphs and they'll ask you for that, where's that inflection point? Just kind of eyeball it. They're going to give you a nice point to pick out. Again, what they defined here is usually it's where the second derivative is equal to 0. It could be where it's not defined, but again, those are going to be really funky functions and not much that we use. So I'm not going to worry too much about those. So here's a graph, and again, you can kind of see here's a concave down part, here's a concave up. So somewhere in between here, and what you're going to see, they occur at, someplace. This one's like at a half, this is at 2. They've got them indicated here, but those, if they give us the functions, we can take that second derivative, set it equal to 0. That's where a potential inflection point is. Again, where the second derivative is positive or negative, that tells us about the concavity. So on one side it's going to be concave up and the other side is going to be concave down, or the other way around. And somewhere along that line we're going to find where the second derivative changes from being positive to negative, and that's where it's going to be equal to 0. So we'll look at a couple examples here. Okay. So if we have the place where we have minimums or maximums, right? If we take the second derivative, this one with the concave down has the second derivative less than 0, which means that it's negative, right? Second derivative is negative. This one is going to be that the second derivative is a positive number. And again, we don't really care what that number is, it's just positive. And everywhere along that concave up or concave down, it will have the same sign. It just, the value of it will change, but the sign will not change, except at about here, where we'll have an inflection point, and that's where the second derivative would be equal to 0. Okay, so inflection points. We're almost to the end. I think I've got one more example to take a look at where we put this together. Again, just more verbiage. If the second derivative is greater than 0, which means it's positive, then we have a relative minimum. If the second derivative is less than 0, it means we have a negative. Meaning the second derivative is negative, then we have a relative maximum. So this one visually would look like this. Negative gives us a frown, gives us a maximum. Positive second derivative gives us a smile, gives us a minimum. Okay, just kind of think through it, remember it, draw a little sketch. I find I draw the sketches because otherwise I learned it backwards oftentimes, and it's hard to unlearn something that you spent so much time learning. And I didn't have a graphing calculator back in those days, so sometimes we spend a lot of times, but if we learn it the wrong way. So here's an example. Okay, we'll be given a function. We're asked to find its critical points. And again, this is coming right out of the homework, and there's maybe 2, 3, 4 of these. I can't remember how many, but they'll give you this function. They'll ask you to find the critical points. What are critical points? That's where the first derivative equals 0. Okay, so we're going to take the first derivative, set it equal to 0, and we get our critical points. Then we're going to take the second derivative to figure out whether those critical points are maximums or minimums without ever having to graph it. Again, I also encourage you to go ahead and graph the original function, because then you'll see your answer is correct. You'll actually be able to visualize it. Or you'll see that you're wrong, which is usually what I do, and I got to flip them. I got it backwards. So whichever way it ends up working. So first derivative, 3 comes down, subtract 3 minus 1 is going to be 2, so 3x squared. Negative 3x, we take its derivative, that's going to be minus 3. Derivative of 7 is 0. So this is our first derivative. We come over here, we take our first derivative, set it equal to 0. We are finding critical points. Critical locations. Critical points. Usually when they say a point, you need both the x and the y. So I forgot to look at, I just gave the x values here, because I think that's all they want, x equals that. So how do we do? Okay, a couple different ways you could do quadratics. You could try to quadratic formula. We could also add 3 to both sides since there's only an x squared, and then we can end up taking a square root. So 3x squared equals 3, right? And then we could divide both sides by 3. So we get x squared equals 1. So then we can take the square root of both sides. And you just have to remember when you solve by taking the square root of both sides, you get both a plus and a minus. So we get a solution at x equals positive 1, x equals negative 1, positive 1, or x equals negative 1. So 2 solutions. The smaller one, well, negative 1 is smaller than positive 1. So we can list those are the 2 places, the 2 locations of either minimums or maximums. Again, at this point, we haven't determined whether they're minimums or maximums, but the second derivative test will help us. We'll take the second derivative of this function, and so that's going to be 2 times 3 is 6. Subtract 1 from 2, we get 6x. So that's our second derivative. And what we do now is we plug in this x equals negative 1. Let's see what sign that has. Second derivative at negative 1. 6 times negative 1 is negative 6. That's negative, right? So that's all we're looking for is a sign. We don't really care whether it was 6 or whatever, but it's a negative value. That means negatives make us frown. That's how I have to think through this. So we have what? A relative maximum. And if you see yesterday's lecture, I got it wrong the first time, but I caught it like 5 minutes later. So that's why I did this one a little bit better. So this is going, so on the drop-down menu, it gives relative minimum, relative maximum, or neither. We're going to say that this one is a relative max. Okay, when we plug in 1, so we take our second derivative, we're going to plug in positive 1. That's 6 times 1, which gives us positive 6. I'm going to emphasize that with a plus 6. Positive things make you smile. Oh, that must be a minimum. And again, I have to draw the picture, or else I'll get it wrong. So this one has to be a relative minimum at that point. And then at the end, graph it. And what you should see, let's see if I can, at -1, we have a max. So it's a cubic that goes something like this, and it's probably going through 0, 0, I don't know, but you would see it. You could okay, yeah, -1, I got a maximum, relative maximum. +1, I got a relative minimum, and it all makes sense. Okay, so we can do it with just the graphing part, but we can also use our calculus, because oftentimes what you're going to find, you get in the business world, a lot of these things, we don't have actual functions, but we have values, and we have how rates are changing and how the rate of change is changing. So sometimes these are all numerical values, and so we can get that feeling whether, again, depending upon what business thing we're dealing with, are we getting towards a minimum and then we're going to pick up, or are we maximizing something and then going to go down? So what should we start planning? Should we be increasing our investment in this product, or should we be decreasing it, figuring we're getting close to a max? Those are the types of things that this mathematics will help you in your deciding. You know, are we going to see some results, or are our results going to wane? That's what these things will help you to see. And that's why if you'll go through and do both, you'll do the graphical, it will stick in your mind more deeply, and then also use these tests, the second derivative test, the first derivative test, and so forth. And then it will sink down in there. And I think, yeah, that's our last slide. So that gets you pretty much through this thing. It's just, again, no real new skill. It's just a derivative of a derivative. So just kind of keep track of that. But what does it do? Second derivative gives us acceleration, so we'll have some direct questions on that. Second derivative also will tell us whether we're concave up or concave down. So that will do it. Also, there'll be some questions about inflection points. Where do inflection points occur? Where the second derivative equals 0. So that's what we can use that second derivative for. Awesome. Have a wonderful weekend, and I'll get some things updated, and we'll be ready.